the von Neumann stability analysis. Before, let us just remark what is the accuracy of the method. You can easily do that by computing the truncation error. And you can do that as an exercise, and you will find that the truncation error of the implicit upward method is of order delta t in time and delta x in space. That means the method is first order in time and space. So now what we want to do for Neumann stability analysis. And we want to do that of the implicit upward method. So we do the same thing as usual. We insert the Fourier mode, that is u hat k n, that is the amplitude of the wave with wave number k at time level n. E to the I k x j. So k is our wave number, J is our grid point. We insert that for ujn, our unknown at grid point xj time level tn, into the equation 37. And then we get the following. The equation was 1 plus c times ujn plus 1. So we do that. So we get then this Fourier mode at the new time level. Minus c times u hat k n plus 1. Now it is e to the I k x j minus 1. It is the upward neighbor. On the right hand side we have the Fourier mode at the old time level. Just it is u j n. So we get u I k x j. Then we can divide by e to the I k x j, the whole equation, and we factorize here the u hat k n plus 1. So then we have on the left hand side 1 plus c, and here we get e to the I k x j, divide, and then we have a minus delta x here. So that gets then into the e to the minus I k delta x. And that is then multiplying the Fourier mode, the amplitude at the new time level. And on the right hand side we simply get then the amplitude for the Fourier mode with wave number k at the old time level. And then we see what the amplification factor is. That is the ratio of the amplitude at the new time level divided by the one at the old time level. So in that case we simply have to divide by this to see that, and then we see then that it's 41, that the amplification factor d of k delta x is equal to this divided by this. If we look at that, we get then 1 divided by what we have in square brackets. It was 1 plus c. And now we use here the Euler's formula. This is cosine of k delta x minus I sine delta x. If we do that, we get 1 minus cosine of k delta x. And then we have here a minus I sine, with this gets a plus. So for that we get a plus c, the I is in front, sine of k delta x. So that is what we used here in between the Fourier's Euler's formula. Cosine k delta x minus I sine k delta x. That is most correct. So then we have the multiplication factor, and then we can do the analysis as we did before. We can compute the modulus, and we can, here it is easier to compute the modulus squared because we have a complex number, and to check whether the stability condition is satisfied. And what is the stability condition that we get? So to do that, we compute the modulus of g of, now we call it beta. So we now use again beta equal k delta x, so that we can write it in this form. And then we get, for a complex number, we can also go directly in the denominator and take the real part squared plus the imaginary part squared. So the real part squared, that is, this is the real part here, and this is of the denominator, and this is the imaginary part of the denominator. So we will square them to get then by that the modulus of g squared. So we take this squared, then we get 1 plus, and then we get 2 times this expression c1 minus cosine beta plus this expression here, the c times so on squared. It gives the c squared, and if we just square also the 1 minus cosine, we get 1 minus 2 cosine beta plus cosine squared of beta. So then we have now the real part squared. Now we add the imaginary part squared, and that is simply c squared sine squared. So beta. Now you see why I did it in this way, because we can now see that we can combine this c squared cosine and this c squared sine squared. So then we can put that in here. We get a cosine squared sine. We get a 1 here. That adds to this with a 2. And then we can factorize 1 minus cosine beta. We have that also here. We can also factorize 2c, so we can simplify this. And then we get the following. So then the modulus of the amplification factor, g of beta squared, is equal to 2. Then we do what we just said. We factorize this 2c1 minus cosine beta that we will also see here again. And then we will get from here, we will get a 1, and here we will get a c. So we get a 1 plus the 2c1 minus cosine that we have. We get the 1 plus c in addition. 1 minus cosine beta. So that is what we get from that. Or maybe you have to look twice to see it, but it is this argument that this and this gives you another 1 here. We take that away. This gives 2 minus 2 cosine. We can factorize the 2c squared 1 minus cosine. And we see that again here, 2c 1 minus cosine, and here we have 2c squared. So then, therefore, we get then this 1 from the left and this c from the right. And the other is the one that we factorize. So if you look at this now a little bit more, we notice in our case the c is positive, of course, we discussed the case where the current number C delta T over delta X, we discussed the case where C is positive. So also the current number will be positive. So that means this is positive, this is positive, this is in the worst case 0, otherwise positive. So we have here something adding something to 1. Get 1 divided by 1 plus something, we get something smaller than 1. Definitely. So this here is definitely smaller than 1 for current number greater equal to 0. And that means that the implicit upwind method is unconditionally stable. We can use any time step with that. But of course we must have this. All is done for positive advection velocity. So the conclusion of this argument is that the implicit upwind method is unconditionally stable. And that means stable for any current number that is stable for all current numbers C greater than 0. 0 is not interesting, then nothing would move, but still included. So that is in contrast to what we had for the explicit upwind method. There we had the CFL condition. The current number had to be between 0 and 1. 1 was the largest one. But here we can do any. That is regarding stability. It is not regarding accuracy. When we want to compute anything, we take a very large time step. We cannot expect any accuracy. So therefore, this tells us it is stable, but it doesn't tell us that it is accurate. So we have to test that and to check that in the computation that we do. So, but now I just want to show you the analysis regarding the amplification factor that we did before regarding the dissipation and dispersion area. So we can write the amplification factor, and also in another way, when we have a complex number in the denominator, when we multiply that with its complex conjugate, we get that also in the numerator. And then we get 1 plus c times 1 minus cosine beta. Then we get it with a minus I c sine of beta. So this is the complex conjugate of what we have in the denominator. If we do that also in the denominator, we get the absolute value. This is what we just computed over there. So from that, we can then later on see the phase angle. The amplification factor we can already see from what we have here. So that is the modulus of the amplification factor. That tells us about the dissipation error. That is then simply what we take from the square root of this here. That is then 42. Absolute value g of beta is equal to, and then we have 1 divided by, and then we would take the square root of the denominator. What we have over there is 1 plus 2 c 1 plus c 1 minus cosine of beta. So that would be then the modulus of our amplification factor. And the interesting thing for this is we can now go with the current number wherever we want. We can also go to very large ones. And if we do that, we can just think of it. If we take very large current numbers here, then that will get large, and 1 plus c will get very large. So we get essentially here c squared in the denominator. As long as beta is not 0, if beta is 0, then we have cosine beta is 1, then this is 0. Then this will cancel things, so we'll get the amplification factor will be 1 for beta equal to 0. But apart from that, we will essentially get a c in the denominator. And so that will go to 0 for c going to infinity, except for beta equal to 0. That is the case just mentioned. So that means we will get full damping with the implicit upwind method as we take very large current numbers. So then we are no longer accurate at all, because we know the exact value should be 1. That is what I just said. It means stability, but it does not mean accuracy. Using large current numbers. So the other point is looking at the phase angle of the implicit upwind method, and that is then what we can get, and therefore we work in this form. The phi is then the arc tangent of the imaginary part divided by the real part. Now, so these will then go when we divide real and imaginary part. This is the same for the real and the imaginary part. So we will have here the imaginary part. That will be then minus current number sine of beta. And the real part will be then this guy here. 1 plus, I think I forgot a 2 there. Sorry for that. I think I forgot a 2. Let's see if that's right. No, it's correct. It's correct. The 2 is only coming from the denominator. Let's see. You can check that. That should be a 2 or not. No, when we go to formula 41, there is no 2. It's just 1 plus c, 1 minus cosine plus I sine. So it's correct. So then we have then here, we take c, 1 minus cosine beta. So that would be the phase angle of the numerical method. And that is then set in relation to the exact phase angle. And the exact phase angle, that was the phi e, that was minus c beta. I remember right? So let's see what we get. Different kind of plots. These are the classical plots for the relative phase error. We take them from the back. So then we see we have large phase errors essentially for all current numbers, and it gets worse as we increase the current numbers. So here we have current number 0.25, 0.5, 0.75, 1. So here we don't have any good results for 1. where the explicit upwind method was exact, so it will go all the way like that. So larger and larger phase errors. Regarding the dissipation error, we see a similar picture. Also, as it should be 1, and as we increase the current number, it gets smaller and smaller, and as we just discussed here, if we take very large current numbers, this will go to 0. So those are the classical plots, and if we look at the Coda plots, then they look like this. Now we have to interpret again in this way, that we imagine that phi is going all the way around from 0 to pi, and that the distance from the origin to the curve that we have here tells us, in that case, what is the phase error. That is the phase divided by the exact phase. So it should be 1, then we would have the phase angle would be equal to the exact phase angle. But we see here it is 1, but otherwise it gets smaller and smaller, and here they all go to 0. So that means all waves, the waves for all current numbers, for the highest wave number that we can represent on this grid, will be stationary. They will not move. That is when we get a phase angle 0. And that gets just worse and worse as we increase the current number. And similar observation for the modulus of the amplification factor, telling us something about the dissipation error. So again here, starting from 0, phi 0 here, we have 1, that's okay. And then it should be 1 all the time, but you see we get here values that are, let's see, here is 0, so this is the distance here. So here we get something 0.3, 0.4 or something, but we definitely do not get 1. So the distance from the origin here should be 1, but we don't get that. So we get a damping. And this is wrong. So then we cannot expect good results with this method. We can only expect good results regarding accuracy when we are close to wave number k delta x equal to 0. That means that we have to have either small wave numbers, that is long wavelength, or we have to have a fine grid, so that delta x gets smaller. So then let us just stop here and summarize what we can say about this method. So the conclusion is this method, implicit upwind method, that it has large dissipation and dispersion errors. Large dissipation and dispersion errors. The dispersion is the phase error, which we saw from the phase angle. Errors for all wave numbers except for k delta x near 0. So that is. And the errors increase with increasing current number. So, it's a very stable method, but not very accurate. So, let us see if we have alternatives. We have. And I want only to tell you about that, not to do with the detailed analysis as that here. This you don't find in the book. but what I'm telling you now is in the books, therefore you can read about it. Therefore I'm more brief on that. So I take that as two remarks now, giving us two new methods. Remark one, and that is another option. Instead of using an implicit upwind method, we can also use an implicit central method. So this comes a little bit of a surprise, because we have seen in the very beginning when we discussed the linear advection equation that the forward time centered space method is unconditionally unstable. It's useless. You check that in exercise 6 by comparing it to the explicit upwind method. It did not work at all. But here we see an example where it works. This is also called backward time centered space method. And the idea is now the following. We have here our grid point J, we have the neighbors J plus 1 and J minus 1. And we have time levels n and n plus 1. What we now do is we want to compute the solution at the new time level, and we use now the neighbors to the left and right at the new time level. Then we get this difference molecule, or this stencil. And that means the following. It's the following method. We take the usual discretization of the time derivative, ujn plus 1 minus ujn divided by delta t. And then we discretize now the space derivative centrally, but at the new time level. So that is the catch. Before we did it at the old time level, but now we do it at the new time level. We have to divide by 2 delta x, and that is 0. And it turns out that actually gives an unconditionally stable method. It's surprising, but it's like that. We can show that by von Neumann stability analysis. So this method is unconditionally stable. So it's stable for all that. In that case, we can take any current number, and it does not distinguish whether C is positive or negative. And if you do the analysis for the truncation error, you will find, since it uses the implicit Euler method, it is first order in time, but since it uses the second order differencing, it is second order in space. So if we would look, I don't do it because of time, but you can look that up in the book. And we find that this method is not, so it is not as dissipative as the implicit upward method. As the implicit upward method. Especially for large wavelength numbers. tends to oscillations. At discontinuities, because there we will need the large wave numbers where it does not actually have this dissipation that would be needed. So in that sense it's less, we call it robust, than the implicit upwind method. In a sense more accurate, but not as robust. So you can look more details up in the book. The second remark is on an alternative to this. So here we used the central differencing in space and the implicit Euler method in time. But there is a class of methods where we use also the central differencing in space, but we use the trapezoidal method in time. And this class of methods that we can also use for other problems, also for parabolic problems, I think there is probably most used, is called Crank-Nicholson method. That is a method that you definitely should know. Two, that is the Crank-Nicholson method. And that uses then the trapezoidal method. That is the one that we discussed for ODEs, which is an average of explicit and implicit Euler in time. And it uses, again, centered differencing. In space, like we discussed over there. And then we get a difference molecule of the kind when we have the J here, the J minus 1 here, the J plus 1 here, and they will be involved. And the same values also at the time level n, and also at the new time level. They will also be involved. So we have then this different stencil, and around the midpoint here, the method is second order accurate in space and time. So that is the good thing. But first I should tell you what the method is. It's the following. We do the same discretization of the UDT as we saw before. But now we take the plus here, we do an average. We have the advection speed little c, take that divided by 2, and then we take the centered differencing first at the old time level, and then at the new time level. Then we take the average, therefore we get here the 2. Plus 1 n plus 1 minus uj minus 1 n plus 1 divided by 2 delta x. And that is equal to 0. So that is the Crank-Nicholson method applied to the linear advection equation. If you would apply it to the heat equation, then you would do it in a similar way. You would do then the discretization for the second order derivatives in a similar way. So this method is unconditionally stable. So this 5 is unconditionally stable. And like method is the same. But now we have the truncation error is now of order delta t squared and delta x squared. So it's second order, both in time and space. So this is now the first method that we see here of this kind. And it turns out when we do the analysis of the truncation of the amplification factor, then we shall see that it has actually no dissipation error. So this does a very good job in that respect. So that means the Crank-Nicholson method has no dissipation error. And a slightly lower dispersion error than the implicit central method that we saw in remark 1. So this makes it, in that sense, quite attractive for wave problems. So if we think about the computational work, when we looked at the implicit upwind method, we saw we got a bidiagonal, lower bidiagonal matrix. Here, both for the implicit central method and for the Crank-Nicholson method, we get a tridiagonal matrix that we have to solve in each time step. This is clearly much more work than we have to do for an explicit method. So that means this adds to the computational work that we have to do. What we get for that is increased stability. We get for all the methods that we discussed now, all the implicit methods, we get unconditional stability. Okay, so then you can read more also on this method, on the Crank-Nicholson method in the book. Just an outlook for tomorrow. We want to continue this journey of numerical methods for the linear advection equation. And one method that is a little odd method, but it should be fine. It has its great disadvantages, but also some advantage, because why it is we use it also for quite complex problems. That is the following. We make the following ansatz. We say the ujn plus 1 minus, and here comes the trick. Instead of taking ujn, we take here an average of the neighbors, uj minus 1n and uj plus 1n. That is the trick. Divided by delta t. You see it is a time derivative, but it is not a usual one. And then we take the standard central differencing for the spatial discretization. That's at the old time level. uj plus 1 minus uj minus 1 divided by 2 delta x is equal to 0. And that we can use from j equal to 1 to nj minus 1. We cannot use it at the boundaries because we need always a point to the left and to the right. We see that when we look at the stencil. The stencil is when we have j minus 1, j and j plus 1. We have nothing for jn. We have n and n plus 1. We have nothing here, but we have only the j minus 1 and the j plus 1. They are entering here and here at the old time level. And we have the value at the new time level. here. So in a sense we have something like that, but we have nothing here. So that has its positive and negative sides. Regarding the boundary conditions, they are entering then by naturally the boundary condition that we have to give. For example, if C is positive, then the boundary condition would be the U0 is the UA for C positive. Otherwise, we would give the UN. And the one that we need is the UN, how to compute the UN, UJN. Let's see, the UNJ, n plus 1. We cannot compute with this formula, but we can use the explicit upward method. So that can be computed by the explicit upward method. So there we cannot use this formula. Okay, so then we have an outlook for this, and we'll see then tomorrow what's the performance of this scheme, where are its pros and cons, and we will see it again later on in the course. Okay, so let's stop here. So we have then seen how we can analyze the schemes by looking at the modulus of the amplification factor and the phase angle related to the exact phase angle, to identify the dissipation and the dispersion errors regarding the amplitudes are damped by the dissipation errors and that the propagation speed is too slow or too fast regarding the dispersion error. Okay, so then we stop here.